studying, and then he's studying the general relativity and geometric analysis mostly in his work. And today he's going to talk about the topology of the region outside black holes. So please take it away.
Thank you, Fabio. So today is going to be a iPad talk. And the reason for this is because it's really a topology talk in disguise. And everybody who's heard of topology, who's had some interaction or experience with it, knows that it's essentially about pictures. And so in order for me to give a talk on this, I needed to be able to draw pictures. And so today is more of an art lesson than really a talk about topology. But so it is. So the main issue is the following. The main issue is this. So this is a black hole. And as you can see, it's rather exotic. So here we have some genus. Here we have a handle. Here we have a Klein bottle. And this is our black hole. This is the event horizon, if you will. And here's the potential well that you see. So does the space outside black holes look like this? Or does it look more like this? So let's have a show of hands. Who prefers this picture or this picture? Who, you know, what do you like best? Do you like the Klein or you like the boring sink?
The first one.
The boring, that right? Okay, one topology. Yeah, you prefer the first one. Me too, right? Yeah, this is a lot more fun than this, no? Yeah. Yeah.
So when you say look like, what observables do you have in mind?
Okay. Okay.
Very quick.
Netta.
Yeah, I think you gotta buy us a drink first. What does that first picture mean? And then I can tell you if you like it or not.
Yeah, so Andy, you just joined us, but my question is, so does the space outside black holes, or is it like this, or is it more like the boring picture we know and we love? So do we like topology and exoticism and all this kind of stuff, or do we like the most boring, most simple possible configuration? Okay, and Netta asked me, well, wait a second, what do you mean by look like? What are your observables? And that's a totally fair point. And on this, I have to concede and tell you, okay, fine, my apologies. Is the space outside black holes like this or like that? As for observables, we can talk about that later some other time. Okay, so of course, say again. Yes. It could be and. Yeah, it will be, as you'll see. So okay, so what do we know? Well, what we know is that we have some solutions. We like them because they're rather simple, at least topologically. So of course, in these cases, it's like this. And certainly not like this. Okay. So just some language, if I consider the edge, right? So I'm going to just delineate some region, and then I'm just going to consider what's outside this boundary. What do I expect? Well, we'll go back to the Greeks. This is, of course, Euclidean space minus a ball. And this blue line is just our favorite friend, S2, two-sphere. Beautiful. Okay. So wait a second. Wait a minute. What are we doing? Well, the Einstein equations are topologically permissive, right? What does that mean? That means these equations are more about geometry than topology. And what does that mean? Well, geometry is the science of things that distinguishes the following kinds of things. So these are geometrically distinct, but topologically identical. And of course, let's use a different color. Apologies to those who are colorblind. These are geometrically identical, but topologically distinct. So this is the cylinder. The actual local geometry of the cylinder is that of flat space. So if you measured triangles, angles, and so on, you'd see the same things as you would here. So my point is that general relativity is, about these equations, and these equations distinguish these things, but they wouldn't distinguish these two things because these two things are geometrically identical, right? So the point being that topology can be as wild and as exotic as you like. Well, in fact, the whole point of the talk is that it's not, but anyway, that's to come. So, okay. Like, first, so now I have to give you some feeling. Okay. So what is exotic? Okay, what is exotic? Well, now take a break from general relativity and consider this just a bit of fun visualization. So we're about to have 5 minutes of just fun visualization exercises. So let's just consider, say, RP2. What is RP2? RP2 is when you take the two-sphere, okay? This is S2, our favorite friend, and you identify all points which sit antipodally, so opposite points. Now, immediately you see that actually, if you do this, then you don't really need to think about this hemisphere anymore because you've identified those points. So what you have is just a hemisphere. But you don't just have a hemisphere, right? Because actually these points are antipodal. So you have a hemisphere where this particular line has been identified. Two points that sit on this line antipodally have been identified. And what that means is that if I draw a curve, if I draw a curve on S2, oh, it's a little thick. If I draw a curve on S2, say a closed loop, we call this L, then I can shrink L to a point, right? I can just shrink it. But if I consider my friend RP2 and I consider a point that say travels from these 2 points, then this curve, although it doesn't look closed, it is closed because these red crosses have been identified. And this curve is certainly different from this curve. This curve, I can contract it down to a point, and this curve, I cannot. Okay, good. Okay, so now that was just a warm up for you. Now we're gonna do something a little harder. Okay, we're gonna think of RP3. So this is S3 to start with. And S3 you can think of as the union of 2 hemispheres. So this is a 3-ball. These are both 3 balls, and I'm joining them along a common boundary, which is an S2 boundary. Okay, and I can also think of this as, R3, where on some big sphere, I'm joining up all the points to a single point, right? So infinity is actually a single point. Okay, so this is S3, and now RP3 is when I've identified points, antipodal points on S3. And so what that really looks like is that, let's say, so now RP3 looks like the interior of this ball, but let's say I am traveling, let's say I'm drinking something and I'm traveling in this direction. What this means is that I will be identified and I will come out the other way, but with my book on its other side. Okay, so RP3 looks like this. So it's a ball, you can think of it as a ball, but as you go towards the boundary of this ball, you come back the other side with a twist. Okay, so this is my high school or elementary school description of RP3. Okay, now let's go a little harder now. Okay, this is kind of fun to draw. Okay, so this is my best effort with the iPad in the time given to draw a dodecahedron. Okay, and now notice that actually if I take this side, okay, let me pick out this side here. I'm drawing this in red. Let me do it a bit thicker. This is a pentagon. Yes. And now notice that I'm going to draw this in a different color just so you can see it. So just like what we did with RP3, where we had this vision of a ball, and we've identified moving towards the boundary of this ball, but with the twist, the same thing is happening here, but just in a little bit more complicated way. So in particular, this pentagon is coming around the other side. And you see, in order for this pentagon to match up with the sides, it's going to be twisted. And what is the twisting? It looks like a clockwise twist, something like turning it upside down. So I'm going to draw it like this.
You have to move it outside. You couldn't move it through, or is that not just an alternative identification?
Yeah,
Would
so
you identify it just like straight through?
no. So the identification is, I don't know how to answer your question other than this is how you define it. Straight through, it's a ball. It's just the interior of it. And it's just that you're moving in one direction, you're coming out the other side. That's how you picture it.
If it's defined.
Sorry, I got a question.
Yeah.
So it's like, now you go from up to down, but you could also go from left to right, right? Because the man that you just actually showed. So the man that you show in, oh, go ahead, sorry.
Every opposing side is identified with this twist.
Okay, but why not like left to right actually flip rather than up down flip?
That's kind of irrelevant. I'm just doing the twist that allows me to identify the sides. You could be twisting it more if you want.
Okay, so but then the question that I got then in show is that the operations that you're actually working with or just like talking about, it's just up to you, right? You define it to be like that. It doesn't have to.
Yeah.
Okay, perfect. Okay, go ahead.
Nothing
Yeah.
has to be anything. It's a free country. It's a free world. You can define topological shapes as interesting and exotic and beautiful as you want. This is just a particular construction going back 100 years, which is interesting because it has similar topological properties as the sphere, but it's not the sphere because it has these non-contractible curves I'm about to draw. So now consider a curve that's in the interior. Let's use a different color. This is a curve lying in the interior, okay? And Peter, right, earlier question, this is just in the interior. So I can contract this happily down to a point, right? However, if I take a curve now that's going from this face to this face, so it's threading through the interior of the dodecahedron, because of the identification, this is actually a loop, right? And so it's not contractible. Okay, so that was my crash course in elementary picture topology, and now let's do some mathematics. Okay, so there is some work, right? So some previous work, and this is work that starts in the 90s, but it goes up to like 2010, more or less, roughly. And it's by lots of people, but mostly Friedman, Witsch, and Galloway, Crucial, a little bit by Wald. It's a bunch of people. The point is, they came up, with a kind of theorem. There's lots of different theorems, but they all kind of say the same thing. And it says the following thing: if MG is a space-time with the following thing: future conformal boundary, scri, you call it scri plus if you like, is simply connected. And in fact, we'll take something even simpler. In general, we take it to be S2 cross R. Certainly that's what it is in Schwarzschild or Kerr. Then this is the null convergence condition. So NA is null. You could take some average version if you like. Right, and average means along a geodesic. Oh. Okay, and 3 is, of course, our good friend. So MG is globally hyperbolic, right? Which means it's foliated by these manifolds V3. These are the Cauchy surfaces of the region of interest. And the result is this. In this case, if you have the following thing, then in fact, pi1 of m is trivial. And pi1 is what's called the fundamental group. And the fundamental group is a mathematical object. There's a group, of course, so there's a whole theory of what that means. The point is, the equivalence classes of curves, where equivalence is defined by being able to be deformed into one another, is trivial. So let's go back to our pictures. This is not allowed because the blue curve in the interior is different to the blue curve that threads through the interior. You know, I can't deform one into the other. A curve that goes like this is also not allowed. So this would be homotopically trivial. This would be not homotopically trivial. So homotopy is just the name that's given to the kind of continuous transformations that we're considering. And a classic example, of course, of something which has, so for instance, if I give you another picture, what this means is that if I have a black hole, for instance, and my black hole looks like this, okay, then suppose I have some curve here. Let me draw it with a different color now, that goes like this. Then clearly this curve, I can deform it down to a point. Let me finish the rest of my picture. Right, so this red curve, I cannot deform it and contract it to a point, no matter what I do to it, but this one I certainly can, okay? And so the point is that then there are different types of loops in this space. And this theorem is telling us, actually, this is not allowed. So if this is trivial, this means that all the loops are the same, they're all contractible.
Martin,
Yeah.
the theorem says nothing about black holes.
Okay, so this is scribe plus, if you like. So this is the future boundary, and the region MG is actually the past of this, which is foliated by V3s, where it's understood that this is an event horizon. MG is the interior. MG is just I plus of scry minus union, or sorry, intersection I minus of scry plus. Okay, so it's everything in the past of scry plus intersecting everything in the future of scry minus. So that's the sense in which there's an event horizon and a black hole. The reason I didn't mention this is because I didn't want to lose anybody in the audience with these kind of technical things. Yeah, always. Always. These theorems are always like this.
The way the theorem works is you just say what the end state is, and you use the actual equations to produce the geometry in the past.
Hold that thought.
Okay.
So, okay, so right now I haven't talked about what I did or what we did with Eric, okay? But so let me draw. This is the exterior of Schwarzschild, scry plus, this is the event horizon, right? This is scry minus. These are the Cauchy surfaces that foliate this thing. And this is what the theorem applies to, and it's telling you that these guys are trivial, right? So the curves are all deformable into one another. There's no differences between certain closed curves, certain other ones. Now, when I encountered these theorems by all these different people that span through 25 years, 20 years of history, I thought to myself, okay, wait a second, what's going on? So we have a space-time. Okay, and then we say, okay, actually, let me just say this space-times, this embeds, right, in a bigger space-time via conformal factor. Okay, so this is what we do for Schwarzschild. So this is the boundary in that case. Okay. And then you say, okay, well, this, I'm just going to assume is like it is in Schwarzschild, it's trivial, right? And then this is foliated by the slices anyway. Okay, and then the theorem essentially says, okay, if you're foliated by these slices and the edge of the space-time is trivial, then in fact the bulk of the space-time is trivial. But does that not sound like begging the question to you? Does that not sound like saying, well, wait a minute, how do you know the future conformal boundary is trivial, right? You're trying to figure out what the topology of the universe is. You're already restricting and saying, no, it's S2 cross R. What kind of argument is that?
Does it run in the opposite line direction? If you say what it is in the past?
Yeah, so both are assumed, yeah.
But it's kind of like saying if you start with a boring black hole, then it's going to be the boring forever.
A little bit. And this was the issue. This was the issue that I felt. These were the emotions I had. And in particular, lambda in our universe looks more or less like it's positive, so far as observations say. And these theorems only apply to lambda equals 0 or lambda is negative. Okay, so the two questions, and this was in the abstract for this talk, the two questions was, what happens when lambda is positive? And what happens when we get rid of this? Okay, those are the two questions. Okay, that's it. That's all we did. We just studied what happens when these two questions, just ask these two questions. Okay.
So there's nothing about the past, assumptions about the structure of the past that would determine that the future was S2 plus.
Well, in this setup for these theorems, these guys are the same. So scri minus and scri plus, they're the same objects from the point of view of their topology. Of course, if you assume the space-time to be globally hyperbolic to begin with, and you assume some topology, by nature of being globally hyperbolic, that means the whole thing is foliated by things which have the same topology, and so therefore the future is going to preserve signatures of that topology. But in this context, these theorems are scri plus and scri minus are essentially the same thing from a topological point of view. Okay, so those were the questions. And now, how much time do I have left? I want to make sure we have some discussion. So I'll try to wrap up in 10, 15 minutes. Should be good. Yeah, okay. So first of all, this was the first observation we made, right? First of all, first point. First point is this. First point is this. First point is naive guess fails. All right, and what is the naive guess? The naive guess is, suppose scri is simply connected. Suppose the region of interest is globally hyperbolic. Suppose some energy condition holds, then is the bulk simply connected? And actually, it's not. This is the de Sitter space-time. Right? So the Cauchy surfaces are all S3. This is de Sitter. So this is a solution to the following equation. Where this guy's positive. This is Schwarzschild de Sitter. So these sides have been identified. Right? So that means I'm wrapping them together to the event horizon. Right? And so if I think of what is a Cauchy surface here, well, this is actually S2 cross S1. So it's like a circle, and each point in the circle, there's actually a sphere. Right? Okay, that's the topology of this red line. And of course, I can take something what's called the universal cover of this guy. and that's just unwrapping the S1. And when I do that, I end up with this. So this is like lots of black holes and white holes stacked next to each other. And the Cauchy surface in this case is the universal cover of this object. And the universal cover of S2 is S2, but the universal cover of S1 is R. So I'm just unraveling the S1. Okay, good. So this is Schwarzschild de Sitter, SDS, and this is de Sitter. And then naive guess comes from considering the following thing. Turn this guy into RP3 by identifying points antipodally. Okay, I can do that. I can take a quotient of de Sitter space, but then I can take a single point here, and then I can consider a small ball around this point, and that I really do mean a topological ball. So I really do mean B3, say. And then I can consider the past of this and the future of this. And then this here is certainly globally hyperbolic. It certainly satisfies the Einstein equations, but it's not simply connected because it's going to pick up some non-trivial curves in the quotienting that you've done. So the naive guess, where you replace the assumptions of this theorem that are appropriate for the context of, say, Schwarzschild de Sitter or de Sitter, then this does not have to be true. The pi1 of the bulk is certainly not trivial. There will be non-contractible curves, you know, in this region. Okay, so that gives us that was what gave us an initial inclination that something will be interesting. Something's going to happen. Okay, now bear with me. I'm going to draw a picture for you. It's going to take me. Yeah. Yeah.
In 3 dimensions.
The spacetimes are 4-dimensional, but yeah, this construction of the quotienting of de Sitter, you can do it for any, RPN is a.
No, I mean the theorem.
Oh no, the theorem, of course, is restricted. Yeah.
It's restricted to 4 dimensions. In 3 dimensions,
Yeah. It's a 4-dimensional theorem, and a lot of the topology that'll happen. For instance, a lot of the things that we'll use as well is that, for instance, if you have something simply connected, say it's a closed manifold, it's simply connected, then it has the homotopy type of S3, and by Poincare conjecture, it's actually homeomorphic or diffeomorphic to S3. So, and there are other things like that when we, in the case of boundaries, etc., where we use 3-dimensional results. So yeah, but yeah, so it's definitely restricted in your dimensions. Okay, so now let's consider the following setup. So you have to bear with me. This is going to take some time to draw, but I think it's worth drawing because it's going to give you a beautiful picture. Okay, so as I said earlier, you cannot do a topology talk without drawing. So this is a black hole. I'm going to describe to you what's going on in just a second. These are now 2 black holes in some system, right, with their respective potential wells. Okay, and maybe I want to consider and be as general as I can be, and maybe I want to consider setups where it's not just one black hole or two black holes, maybe it's just some arbitrary collection. So one thing, other than the fact that we had some assumption on the topology of the future conformal boundary of the space-time, and the assumption that lambda was 0, another thing that bothered me was that these situations, these theorems were proven in the context of asymptotically flat spacetimes, which are not spacetimes that describe our universe. Our universe is a cosmology. There may be multiple black hole regions. Maybe they're isolated. Maybe they're interaction. Maybe they're a subsystem. There are galaxies. But Scri plus and Scri minus is for a single gravitationally isolated system, not describing a whole cosmology. So I wanted a theorem that captured these notions, but that applied actually to the universe. So this is a collection. I'm not going to draw the potential wells in each case, but this is the kind of setup that we wanted to cover. And then this is, we'll call these sigma 2s, these surfaces. Sorry, this is sigma 2, say. Sigma 1, and I'm not going to draw a sigma for this one. And this is gamma 1, gamma 2. Okay, and now I'm going to make some assumptions, because as you know, you don't do anything without starting assumptions. So assumption number 1 is going to be each gamma I separates. What that means is that there's a well-defined inside and outside of gammas. V is the Cauchy surface for the whole space-time. And I'm gonna, so these regions, these are the black hole regions, obviously. This is B1. B2 is actually disconnected, so 2 black holes. And this is, many black holes. You could call this, all of this B3.
So what's the difference between sigma and gamma? That has the boundary of sigma?
No, so let me finish what I'm saying. So sigma I is the boundary of the black hole, if you like, of B I. So sigma models the cut between V and the event horizon. Okay, so in the case of Schwarzschild, it's an S2, but if you have a toroidal black hole, say in high dimension, it'll be S2 cross S1, for instance. Okay. Gamma is different. Gamma is actually constrained. So gamma I topologically is actually S2. And gamma basically serves as a surface which is the boundary of the region that you can consider to be gravitationally isolated from the other black hole collections. Okay? And so the idea was that suppose you're traveling in a rocket, in a spaceship, and you're hovering some galaxy or black holes or whatever, then the idea is that you can somehow think of some big enveloping sphere as being something which bounds whatever is going on inside. Okay, but you're assuming that thing to be S2. Okay, this is our strongest assumption. But as I will describe to you, the theorem badly breaks if you lose this assumption. The proof breaks in all kinds of ways. So this is important.
You need some sufficiently large surface.
Sphere. Sphere. If it's a surface, it's not enough. You need a sphere. Exactly. Okay, so those are the assumptions. And crucially, by the way, one very nice thing about this, and essentially what makes the proof possible, is that there's no assumption on sigma I. No compactness assumption, no connectedness assumption. Just a separating assumption. And a very weak regularity assumption. It's C0, in case you're interested. This makes it possible to prove the theorem, because we'll actually use, I'm not going to show you proof, but we'll use this. The weakness of our assumptions on sigma I permits us to apply some of the lemmas we prove in a covering space-time for these kinds of scenarios. But anyway, the point is, this guy is very nice, but this is, there's very little assumption. Okay, now what's the final assumption? The final assumption is where my picture skills are going to be really put to the test. The final assumption. Oh, by the way, I should draw in the meantime, I should label some things. So, these are the black hole collections, right? So the region in between the black hole collections, right? This region here, we gave it a name. We called it the core. And the reason is because, and we labeled it C, and it's defined as the intersection of all the E2Is. I should have added a fourth thing here, labeling thing, which is that, so V is the union of E hat 1I separated by gamma I and E2I, where basically for each I, everything in this region here would be considered inside E2I, and everything inside, so let me use a different color, everything inside would be considered E1I hat. Okay, and the hat determines or is supposed to denote that you're considering everything inside. And if you're just interested in this particular region here, then you can denote this region just to be E1I, okay? And then the whole guy inside is E hat 1I, okay? The point is that the separating assumptions of the gammas and the sigmas allow you to actually denote these sets. And so the core is basically the region between the black hole collections. And so it's not hard to see that this actually ends up being equal to V minus the union of all the black hole regions. Right, so these are all the black hole regions, and this is, modulo boundary components. But the point is, this is what we mean by the core. So this is the core, okay? Okay, now the main assumption. Now the main assumption, and as I said, this will take me some time to draw. The main assumption was, in a simple drawing, was like this. Suppose you had, so this is time, okay? Suppose you had some black holes, and they're not too far from one another. These are your black holes, okay? Well, our assumption was actually, asymptotically in the future, they get isolated. So really what ends up happening is that maybe they merge, maybe they merge into one another, whatever, but basically they become isolated. That was the main assumption. This is our assumption, our assumption.
Do you have the Sitter space in mind?
Sure, you have some kind of expanding, cosmology possibly, and you're thinking of these things as being isolated eventually, okay? Now, this is not a mathematical assumption. Now I'm going to draw you how we translated that into a mathematical assumption. And this is the difficult picture of today. And after that, I promise no more pictures, unless you want some. Okay, so what does it look like? Of course, this is time always moving forwards. Okay. 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 So this is a black hole. Okay. Okay, and this is another one. Maybe this system has two black holes. That's okay. They're in some configuration. That's okay. Okay, good. And remember, these surfaces, gamma, they serve to denote the region inside of which is isolated from the other black holes. Now, what does that mean? What does that actually mean? Well, this is the best way we found to formulate this. So what color should I use for null geodesics? Let's use blue. Remember, this is an S2. I'm allowed to shine beams of lights inside and out. Suppose I send a light beam in this region, okay? Good. Now, of course, as we heard from Alex earlier, we can have all these kind of things happening. We can have some orbit. All right, and this is somehow the end state. Of course, we can fall inside the black hole as well. This geodesic never comes out. Okay. So this is fine. The assumption says inwards directed null geodesics emanated from gamma I for each I either cross into the black hole regions or they're future complete. But in particular, they stay in the domain of dependence of E2I. And what that means is that the following thing is not allowed. So I'm going to draw it in red to say it's not allowed. It's not possible for a null geodesic to go inside and cross this region here and go into this other region. And this is our way of saying the far apart. Okay. So this is the assumption. This is the main assumption.
So some black holes will be close enough that they'll attract and fall out. Some are far apart.
So there is a collection of black holes. There exists surfaces which indicate or which identify the boundary of a gravitationally isolated region. And what that means mathematically is that if you send null geodesics from that surface inside those regions, they stay in the relevant domain of dependence. They don't enter these other black hole collections. So if you had a universe, okay, let me draw you a picture. If you had a universe that looked like this, where you had distinct black hole collections, but the black holes remain close to one another, then our assumption would be wrong. Our assumption wouldn't hold. Basically, what you need, this wouldn't work. What you need is you need the space-time to have the property that eventually you can think of some surface as being the boundary of a gravitationally isolated region, meaning what I said before about the geodesics. So this is not allowed, but this is allowed. So for instance, if you had loads of collections like this is okay, and maybe one here, but they have to be far apart. This distance has to be big enough.
Sorry, so maybe to answer the question. So suppose that you just draw
mean, how do I say, you can always choose bigger spheres, if you will, if it's the case that a beam of light will cross between one gamma eye and another gamma eye. You can just choose a bigger gamma eye. That way, like it's a little.
Yeah, once you have a gamma eye, there's obviously a freedom as to whether or not you picked a gamma eye. You know, there's obviously freedom with which, once you've identified one, there's going to be a family of them. But in a setup like this, the point is that in a setup like this is that if you pick the gamma eye bigger and bigger, then this gamma eye, the inwards null geodesics are not going to be isolated and, you know, behaving with respect to this region, right? Now the region of interest for this gamma eye becomes these are the black holes.
Sure, but what I mean is you could always just choose the gamma eye, for example, to encompass all 4 black holes. Is that right?
Absolutely, absolutely. But then that would mean that the universe goes up and is infinite because it gets bigger, right? And then you can say, okay, just choose gamma to be this. That's okay, but that's only okay if this region here, if the complement, if you like, of this region is big enough. And that could mean it's infinite, or it could mean whatever other black hole collection is really far away.
Less teleological than saying that you know topology is abstract.
Well, give me 30 seconds, I'll show you.
So the idea, if it can escape, if it's big, if the sphere is big enough, then you hope that if a photon can escape from gamma I, it could go into a gamma J.
No, the
Does
assumption,
this happen in the time of the universe or something?
the assumption is that your universe looks like this. So although at this stage, sure enough, you can shoot in a null geodesic and eventually it can go into this black hole region, and that would be a problem. But the assumption is eventually the universe looks like this, meaning that I can consider some gamma such that the null geodesics will never go into those regions because they're so far apart. That's the assumption. So Nada asks, well, that's a little like an end state assumption. Are there 2 answers? Of course, but as you know, you can't prove a theorem without an assumption. And so the question now is, what kind of assumption do you want to make? And this is obviously far more intuitive and nicer than assumption scry is exactly fixed to be this. Then let alone all the point about we don't actually need to even have a space-time that can admit such a scry or whatever. Then the next point is that there is a moral to this theorem, which I'm about to give you, as I'm about to give you the punchline. The result says this, that these were the gammas, right? And the result says, well, actually, you're allowed to have any topology you want. The theorem doesn't restrict you at all, which is much more intuitive in my mind. Be all kinds of topology you want. However, the moral is that, so by the way, mathematically, this means that the pi1 of V is the pi1 of C, right? So all the topology of V is inside C, right? And so what this means is that these regions here, right, are indeed trivial. Topologically trivial. So what this is saying is that there's a kind of quasi-local version of topological censorship which holds in this case. We can't restrict the topology of the universe. The universe could have any topology it wants. However, the moral of the story is black holes do not contribute. In other words, if there's topology in the universe, it's there in the Cauchy surface for the universe. It may end up leading to collapse into a black hole, whatever, but so long as the black holes are isolated from one another, and you can draw these big S2s that delineate the boundary of interest and that bound this gravitationally isolated system, then the blue regions are indeed topologically trivial. So the teleological aspect is that we're not being greedy here. We're not going for topology as trivial, which is what you do get when you do the other theorems. We're saying topology can be anything, but whatever it is, if the black holes become isolated from one another, etc., then some form of local topological censorship holds per black hole collection. And so morally is like black holes don't contribute to the topology of the universe. If there's any topology in the universe, it was there from day one, and it's not something that's created by, or it's not something that's instantiated by the presence of black holes. It's time for me to finish, I think. Thank you for your attention.
Thank you for
So you say that local text, no, are there other waiting?
no, they're not.
So where do wormholes fit into this scenario? Because one of the things that we're trying to figure out, let's say with observations, is are there wormhole configurations that could be observable?
Yeah.
And you're saying that the topology around the black hole is very simple.
Yeah, so let's draw Sheps' question. This is a wormhole, right? Okay.
Now, in your world, does that count as being simple, or is that one of the?
Oh, that's definitely not, because it's got a curve that threads through the interior.
Okay.
This is not trivial. So our theorem says, if you have the assumptions that you have, then this is not allowed.
Is that because those black holes could never, their gammas could never be distinct? And which assumption is violated?
Which assumption is violated? Okay, good. The assumption that's violated is that for there to be a meaningful gamma, right? So you can, there's two ways of doing this, right? If you try and say, okay, gamma is like this, right? This is gamma I, this is gamma J. Okay. Then clearly there's an issue, because I can send a null geodesic inwards, go inwards like this. And if I compute what happened, or if I, at later times, this guy could thread this region and could enter into this black hole. And so obviously our assumptions are violated there. So this way of attributing the gammas wouldn't be a good way of doing it. And that would immediately violate the assumption. Yeah.
I'm so confused now. I thought you said that this theorem applies outside of the black horizon, and this is actually towards the wormhole.
No, absolutely. But I'm drawing a picture in which it is.
Okay, so even if it's towards the wormhole, and you're saying, but then it's only behind the black horizon, because by definition, I'm not the square plus. If you wanted to go in one.
Yeah, but well, of course, but the question is, can we observe them? So I'm drawing a scenario where there's a traversable wormhole. If the wormhole is behind the event horizon, there's no discussion to be had.
I guess I don't understand. In what sense you have a black hole here, like where's the region that's not accessible to square plus?
Well,
Sorry, couldn't hear you.
I
Where is
don't
the
understand
region?
that there's a black hole, then where's the region that's not accessible to square plus?
well, remember, there's no square plus in the theorem.
Well,
So
there's no black hole.
And what's the black hole? I thought
Yeah.
future law.
no, I mean, it's you can define something which looks like an event horizon, right? So it's a null hypersurface with so on, such properties. That's the boundary of some regions, for instance, the core. If you had no. So let me show you. So take take the simple case of Schwarzschild de Sitter. This is a universal cover, right? Now, in this case, the gammas would be here, say, this is gamma 1, say, and this is gamma 2, say. Okay, and then this region going all the way now would be E21, and then this region that's going all the way would be E11 hat. Okay, then you can and say this is your sigma, right? So quasi-locally, you're recognizing it like an apparent horizon. And then let's call this guy, let's call this F. F12. Then, yeah, so what I'm, sure. What I'm doing is I'm taking Schwarzschild de Sitter, which is where all this is coming from. I'm going to identify things in Schwarzschild de Sitter which don't refer to the event horizon. And I'm going to use that as my notion for a black hole. And then I'm going to assume that that is a meaningful way of speaking about a scenario where I don't actually explicitly mention a scribe. So, for instance, the domain of dependence of this region here, right? The domain of dependence, the future domain of dependence of F12 is this region here, right? I draw it in small. This is it. Okay. And the black hole in the event horizon in this context is simply the boundary, as always, of the past of this region, right? But then that will include this guy, this boundary component. And it'll include this boundary component, correct?
Never one another. There's a sense in which you are making reference to some kind of a future incidence of this.
Absolutely. Absolutely. You need something.
Wait. So then that goes back to my earlier question with the black holes and Sheps question, which is what, I mean, in what sense are those black holes? The thing that you do.
They're black holes in the sense that the causal geometric structure associated to the setup of the theorem, so the gammas, the sigmas, the EI, the E2Is, are exactly what you would expect them to be if you pictured them as being embedded in a surface that has a scribe plus. You're taking the causal geometric properties that you know hold in setups like this. You're abstracting away from scry because you don't want to talk about scry at all.
I don't know how to abstract away from scry for different objects and definitions that all different objects.
Well, I'm just giving it to you now. This, right? This has, we'll take the connected component, right? The connected component to sigma 1. And that will be a causal geometric way of talking about this surface here. And I've just defined this surface without mentioning scry.
You mentioned gamma, which refers implicitly to scry.
No, there's no. Gamma, no. There's no reference to scry in gamma. Right? Gamma is just saying that the future, the null geodesics that emanate from this, their future completes in D plus of E2, E2I union E1I. So they're future complete just in the domain of dependence. So there's no talk of scry.
But they don't enter those the other.
Absolutely,
Yeah.
absolutely.
Is that, sorry, I mean, maybe I don't want to be on this, but isn't that an implicit reference to sky?
No, you see, scry is a useful concept, no doubt, but you can abstract away from scry and just understand the causal geometry of what's happening, say, in this diagram, as I'm doing to you right now in front of you.
So you're saying, I think, Martin, your assumption about the non-existence of connecting geodesics says something about the far future, but it's not enough to completely specify scry. Is that the point?
Yeah, that's the point. That's the point. It's that this smells and looks and tastes like scry, but I'm not writing scry down. That's the whole.
Not though, you're supposed to write.
Why not? Because
It doesn't seem to me like you would have been able to get any of this whole set of concepts across without understanding that it's.
Well, that's simply because everybody thinks in terms of scry, and I'm trying to show you that you can abstract away from scry specifically, think about the causal geometry of what's going on here, and then come up with ledger concepts that don't reference scry and that are just defined in terms of the initial data and the causal geometry of the setup. I agree with, there's no, I could show you the theorem and replace the assumptions with a scry, but the point was that what's really going on is causal geometry. It's not the past of scry. And in particular, I don't want to assume anything about the topology of the past of scry, about scry. I don't want to say scry is a surface with such and such issue, because mathematically, it just doesn't.
But your slice there has to be in a region where the geometry is supposed to have form, right?
Definitely, yeah. This kind of thing only makes sense.
You sort of know what scry is by the time you get to this point.
That's right. Yeah, there's an implicit. So let me say it a different way. Scry is, we're assuming our assumptions apply to spacetimes to which you probably can associate a scry. But the point was that we wanted to get rid of the actual object scry itself. But I agree with you. Implicit, and Nada, and Peter, all these comments. Implicitly, these kinds of spacetimes are inspired from the examples we know, where you can associate a scry. But we went through the mathematical process of getting rid of scry in our equations and our theorems, just so we can abstract away from things like scry and just think about purely causal geometrically, what is the key thing going on?
You might not recognize this is an actual hand ray, which is different from the Zoom hand. So
yeah,
we're all used to actually after 2 years. So I wish I think I'm trying to color it gold, but then you would recognize it more. So you asked it. I'm just a humble astronomer, right?
Yeah.
And so I clearly need to learn a lot more about scry and all this stuff. But at the very beginning, you said, does black holes look like this or like this? Or is the topology outside black hole this or this?
Yeah.
And so I think of wormholes as being that, more exotic.
Okay. Yeah.
Okay? And I'm not sure if you think of it that way.
No, that's fine. We can think of it that way. Yeah.
And there are some papers recently in the literature written by people here at the BHR, like Martin Lesourd, for example, who say it's possible to have photons that go through a wormhole and come back out.
Yeah.
And you can have multiple rings that can be visible.
Yeah.
And I'm trying to understand from an observational perspective whether we can answer this question. And then I'm trying to ask, how does that fit with this purely theoretical approach?
So
understand
yeah, so there's two ways to answer your question. The first is, okay, from the point of view of our theorem, you can have wormholes in the intergalactic regions, and by that I mean the things that aren't in the black hole collections. So it's perfectly reasonable to have a wormhole in this region between two large black holes, say, from the point of view of the theorem, right? But then a more refined answer would be to say, actually, there's something that happens when you have a wormhole. which is that suppose you have a wormhole, okay? Then what happens is that if you actually consider the universal cover of this guy, which is the space that is defined mathematically by a kind of larger version of this space, which by identifying parts of it, like I was doing in the earlier part of the talk, I can create this space, the wormhole space. If you do that, then you end up with some bigger space, whatever it is. And it turns out that when you have such a thing, if this object here, let's call it V tilde, and let's call this V, if V tilde is non-compact, right, which means it's spatially infinite, which means essentially you're not in a spherical universe, say, then having such a thing will actually lead to a null geodesic being incomplete. So the presence of wormholes, when the Cauchy surface has the topology, which means you can unravel it in this way, which in this case you would, that tells you that there should be an incomplete null geodesic. And then there are other theorems other conjectures in the mathematics literature which tell you that such incomplete geodesics will always lie behind an event horizon. So you will never actually see the incomplete null geodesic. And so from that point of view, you'd say wormholes cause singularities, or they cause incomplete null geodesics. And if things like weak cosmic censorship is true, which is this big open mathematical conjecture, then the event horizon that's created by such a wormhole should actually envelop the whole wormhole, and you shouldn't be able to see it. So basically, if wormholes are lying around the intergalactic regions and they're observable, then something is not playing nice between theory and observation, and there is some conjecture that doesn't quite apply to the real world, or there is some thing about the real world that makes it fall outside of the scope of these theories. So in other words, the mathematicians would say you can't observe a wormhole if our conjectures are correct. And then if you find one, say, then you will say, okay, but what's going on? Because I found one. So your conjectures either are wrong, or the spacetimes that we live in do not fall within the realm of applicability of your theorems or conjectures.
I see Priya in her head.
Yeah.
And that's like a real.
Yes.
Yes, Priya.
Yeah, hi. So very interesting, Martin. So I had a related naive observational implication talk. So it looks, astronomically speaking, that we might be just, galaxies might just be littered with multiple supermassive black holes. So how does the theorem take into account multiple black holes, or just the argument is applied one black hole at a time?
Yeah, so that was kind of the whole idea behind our theorem, was to make it applicable to black hole collections. So if this is a galaxy and it has loads of black holes in it, then the theorem is okay, so long as the other one, which has loads of black holes in it, is big enough. This distance is big enough. If this
Like,
is
big enough compared to what?
Well, big enough is my colloquial way of trying to capture the assumptions in the theorem, which are that the null geodesics emanating from this surface, so let me draw a different color, right? That the space-time is of the form that if I have for sufficiently late times, so waiting for this distance to get big enough, the null geodesics that are inward directed from this surface gamma, which you could think of as being some big enveloping sphere around a galaxy, say, okay?
Yeah.
These null geodesics don't go into these other regions. So the space between them is too big.
Right.
That's,
I see. Right. And so, yeah, I see what you're saying. But what about the, a supermassive binary? that is merging in the process of merging, which is, you know, a long drawn process. So what is happening in that case, this null geodesics, there will be interference, right? So if you have two really supermassive black holes in the center of.
There can be interference, but the point is that at the very, very late times of the universe, then maybe this is no longer a suitable surface. Maybe there is a bigger surface, right? Call it, maybe it's a new gamma, where then you can think of this whole thing as a collection, and that will be far apart. That distance will be big enough to the nearest one. So basically, the theorem is something like this. If the universe is such that black holes that may form end up being gravitationally isolated from one another in the sense that inwards null geodesics directed from some surface yet to be defined or identified are future complete with respect to the domain of dependence of the sets associated with the separation of the big V Cauchy surface of the spacetime in terms of the gamma. If these guys are future complete, then, or if they fall into the black holes, but the ones that are inside the gamma, then the theorem will apply. So in other words, if these, you know, if these galaxies get isolated from one another, then it's okay. But if they remain close somehow, then it's not okay. Then the theorem doesn't work. The theorem doesn't apply.
But I mean, just making gamma encompass the entire visible universe then doesn't work. That would be the only way forward, right? If you have many galaxies.
If gamma encompasses the whole observable universe, then yeah, then you're going to have to change what we're talking about a little bit, because the idea here is that this is just a surface in the universe that separates these regions.
Martin, Jane, Priya, I think we need
Thanks.
to.
Yeah, it's
All
actually
good things need to. We have promised lunch for everybody who's local. And thanks those joining remotely. We're going to take a moment to thank the speaker. And we have lunch here, and we're going to maybe reconvene on the steps outside.
Sure. Thank you, everyone.
Thank you. Great.
Here, I'm gonna go.
So